Okay, so hello and welcome back. So in the previous video we talked about all of these SI basically prefixes and the SI base units and so on and so forth. In this video we will talk about the SI base units, meaning that we will talk about a little bit about the definitions and so on and so forth. So the SI base unit, the initial units of the metric system which eventually evolved into the SI system, were established in France during the French Revolution. The original standards for the meter and the kilogram were adopted in 1799 and eventually by other countries. This section introduces 4 of the SI base units commonly used in chemistry. Other SI units will be introduced in subsequent chapters. So one thing that you need to understand, of course, there is actually a lot that needs to be understood about these systems of units. There is something called a system of units. Now these systems, for example, a SI is a system of units. What that means is that the SI system, basically it contains everything that you need for measurement. It contains all the prefixes. It contains all the prefixes. It contains all the basically unit definitions. And basically all the necessary agreements that we need to have in order to be able to use this as a system of units, or as a system of units. Now this SI system was primarily known as the metric system. Now if you want to know more about, and of course I think I need to do the same, I haven't done that yet. If you want to know more about these systems of measurements, which in my opinion is pretty important, because and the reason why that's important is that basically eventually you will need to convert between different systems. For example, between the English system, the American system of units, or British American system, as you can see. The US customary units, that's the term I was looking for. The US customary system, there is the British system, and as it turns out, the US customary system has actually been adopted from the British system, and all of these systems have initially been taken from the systems that Romans used to use thousands of years ago, right? And so if you want to know the history of all of these, basically the history of all of these units of systems and everything, you need to go to the best place that I have found is there is not much that you can actually find on this subject. People usually don't know much about this. You can for example go to Wikipedia, but there I went there, but I got confused because the system, basically the way that Wikipedia has been written is more of a confusion type of thing than giving you information. meaning that, for example, here you want to know about the United States customary units. And suppose that you don't know anything about the United States customary units. Now, it is basically assumed by the system of Wikipedia that you already know too much about too many things before you go to Wikipedia. For example, they talk about, as an example, let me read you a couple of things, a couple of lines, and then I'll tell you what I mean by that. So the United States customary units are a system of measurement, right? So right off the bat, they give you system of measurement. So you don't, I mean, the system of measurement, if you actually open this in a new tab, what you will see is that a unit of measurement, or basically level of measurement, or whatever, a unit of measurement is, now of course it's not giving me the right page probably, but as you can see, there is already this much information over here, and if I don't know this, then of course then the problem is that I will not be able to understand this sentence here, because this term has been used in this sentence, right? So they tell you all right off the bat, they give you a term that you might actually not know much about. For example, the United States customary unit are a system of measurement, and you don't know what the system of measurement is. It's a big term referring to a big concept, large concept, so there is no way to know that really. Commonly used in the United States. The United States Customary System, or USCS or USC, developed from the English units. Now again, you need to know what the English units are. And that's again, in and of itself, you would need to read up on that probably a few days until you understand it, which were in use in the British Empire before the US became an independent country. However, the United Kingdom's system of measures was overhauled in 1824 to create the imperial system, which is again another system over here. That's a large system in and of itself, changing the definitions of some units. Therefore, while many US units are essentially similar to their imperial counterparts, there are significant differences between the two systems. Now, believe me, I have been trying to get the hang of these 2-3 simple things. You would need to open at least 12-13 tabs on Wikipedia, right? And then you would need to read all of them. And again, in those 12-13 tabs, meaning 12-13 pages, again there is new terms, meaning there is some sort of, you could imagine that it's like a system of nested new terms inside new terms, and so on and so forth. So it would take you forever, and you wouldn't, at the end of the day, you wouldn't understand it. Now, there is another problem with Wikipedia, and that is everything that you can see written here is written by somebody who thought that they knew enough about this subject. Now, of course, there is the possibility that, for example, if I think that I know enough about this topic, I can read it and I can edit it, and then I have to send my edit back to Wikipedia. Then somebody else has to basically go over the content that I have written, and it has to be probably acknowledged by somebody else, and that again becomes knowledge. And as it turns out, Wikipedia is today the best place that we can find on the internet to find information, and the information is usually written by people like me, who, who think that they know much about the topic, but then I might probably have some problems with that topic, right? Meaning that it's not, for example, it's not written by somebody who basically holds a PhD on system of units or some related area. You know, then not, it's more, in most cases it's just not like that. So then there is that problem that you cannot really, in some cases, you cannot really, at least 100%, trust what you read on Wikipedia. Now, these two problems, and there is only these two problems with Wikipedia. There is no more problem that you can see. It's fundamentally, it's a great website. It's a great place for finding information. But these two problems are there, and these are basically the types of problems that usually are deterrents, meaning that they don't let you use it. I mean, if you know a little bit about something, you can go to Wikipedia and probably find some information. But if you don't know anything about the topic, then of course you cannot go there and start reading. You wouldn't get anywhere doing that. Another website that has, in most cases, solved that problem is the Encyclopedia Britannica. So on Encyclopedia Britannica, what you can see is that, for example, over here, I want to know something about system of units, or customary, or US customary system of units. So measurement system, the English and United States customary system, for example. Now, if I click this result, of course there is a problem here that you have to pay them around a couple of dollars a month, which is not a problem. It's like $4 or $5 a month, and then you can have access to basically to the as you can see, you can join, and then you have 7 day free trial, and then $61.95 per year, which is, well, I mean, I would pay this money. It's actually worth it. But now it took me to this page, and I didn't really want to go there. Okay, so if I go here, so you can see that, for example, if I go for system of units, for example, the International System of Units, right? So over here, what you will see is that it gives you, well, first of all, you have the International System of Units. There is no link, there is no nothing that something links to this page or this or that. And if you pay the money, all of these ads will go away. So these ads, they will take care of these ads for you. So as you see over here, these ads will be taken away, and you will have a clean page to read. And then it tells you that alternative titles are for example, SI System, System International, and so on and so forth. So it says that International System of Units SI, International Decimal System of Weights and Measures, derived from the extending the metric system of units adopted by the 11th General Conference on Weights and Measures in 1960. It is abbreviated SI in all languages, right? So this is something that you can understand. There is not much problem with that, meaning that you don't have to actually go to any other page except that, for example, for the metric system. And then it says that rapid advances in science and technology in the 19th and 20th centuries fostered the development of several overlapping systems of units of measurements as scientists improvised to meet the practical needs of their disciplines. The early international system devised to rectify this situation was called the meter kilogram second (MKS) system. The General Conference of Weights and Measures (CGPM) added 3 new units, among others, in 1948: a unit of force, the Newton, defined as that force which gives to a mass of 1 kilogram an acceleration of 1 meter per second, a unit of energy, the joule, defined as the work done when the point of application of a Newton is displaced 1 meter in the direction of the force, and the unit of power, watt, which is the power that 1 second gives rise to the energy of 1 joule, and so on and so forth. And then it gives you some information about the system, and it gives you all the relative information that you need, right? And then, so you have, for example, this is the international system of units, base units, as you can see, 1, 2, 3, 4, 5, 6, and 7, the exact 7 units that we had in the book. And then for the length, you have these units and their abbreviation, their number of meters, for example, and then approximate US equivalent, right? So that they have taken care of that as well, and capacity and so on and so forth, metric conversions. And so what I mean to say is that if you read just one article here, you will manage to, at least, even if you don't know anything about the topic, you will manage to understand what it is that you're reading, right? But on Wikipedia, it's not possible, of course, if you don't know anything about the topic that you want to read. And for those, and there is one more problem that I pointed out to, which is basically these articles over here have been written by experts, senior editor. For example, this article was most recently revised and updated by Eric Gregerson, senior editor. And these senior editors, they know, for example, if this Eric Gregerson edits this article, he knows about this topic. It's not like, for example, just some random person writing something on the internet. It's not like that. I mean, writing random things on the internet is okay as long as you're writing a blog or something and people are reading your blog, that's okay. But when it comes to scientific things, it has to be something that you can trust. Otherwise, you would either get confused, or you would not get anywhere, or you would learn basically wrong information. It's just not worth it. Pay $5, $10, $6, whatever that was. The subscription is $61.95 per year. That is only $61.95. $61.95 divided by 12 gives you $5.16, not more than that. So I suppose I will actually do that myself, because I'm tired of searching for information on the internet. But with that said, I should also add to this that not everything it's not like you can find everything on Encyclopedia Britannica, but most topics you can find good articles there, and you wouldn't have to just keep moving between internet pages here and there. It's just not worth it. Okay, so now that is about finding information, and so there is basically, as I was discussing here, basically there has been this metric system, and this metric system, as we read on that article, it's been, I don't know, it's been devised or at least in use in 1799 or so in France, and then other countries have adopted that as well. And then this metric system, for some reasons that I don't remember right now, I used to know the reasons, I don't remember them right now, it has I think a few decades ago, it has evolved into the SI system. And this SI system is basically the system that is used in between scientists. Between scientists, this SI system works pretty well. Everything is basically international agreement, and everything is in place, so you would have no problem using that system. And so now let's get started with length. So it said that the standard unit of length is both in SI and original metric systems is the meter. A meter was originally specified as 1/10 millionth of the distance from the North Pole to the equator. From the North Pole to the equator. So, on the Earth, of course. And, well, of course, as you can see, that the unit is not that precise, because if there is changes in the shape of the Earth, or the lengths on the Earth, or on the surface of the Earth, and so on and so forth, then the unit is going to be, of course, the unit is the standard is going to change, and it's not supposed to be like that. Meaning that you just don't take something physical out there in nature, for example, a piece of stone or a rod, and then take it as 1 meter, because the rod can go through decay, can go through all kinds of natural phenomena. The length of that rod could change, it could get bent, and so many different things could happen to that rod. You could even lose it, right? Somebody might steal it. So now what they have done, they have over time, they have had many different types of conventions and agreements for and definitions for meter, including this distance from the North Pole to the equator, 1/10 millionth of that distance. But then once they realize, but once science and technology basically improved a little bit, once science and technology improved a little bit, it was actually possible for science to define the meter as the distance light basically travels in vacuum in, for example, 1/300, approximately 300 millionth of a second, right? So this is now, and you know that the speed of light has never changed since probably the beginning of time. The speed of light is something that nobody can steal it, nobody can bend it, nobody can do anything to it. And so now what they have done is that they have defined the distance light travels in a vacuum, in vacuum, basically in 1/299,792,458 of a second. And moreover, now you can see that that the meter is actually based on the unit for time, right? Meaning that if you don't have this unit for time, of course, this would be meaningless. And there was problems with this unit of time in the past as well, because the time was originally based on the earth going around the sun, or the sun going around the earth, or the earth going around itself, or things like that. And what they have observed is that over time, it seems that this time has kind of changed over time. And so, since they needed a better unit for this kind of, they needed a more precise unit, a more accurate and precise unit for time, and more reliable, of course, then they have now used, for example, the radiations of the cesium-133, for example, atom, in order to define a second. Now, the second is defined based on those radiations of the cesium-133 atom, which is a stable thing, and those are called now atomic clocks. So time is now measured by atomic clocks, and that doesn't actually change in an eternity. It doesn't even have any tolerance. Then they have used that definition in order, and then they have also used the speed of light in vacuum in order to define the meter. And this way, everyone around the world has access to this unit. They can reproduce it in a lab. They can use it without any problems. And so, of course, the speed of a second is going to be a second wherever you go in the universe, and the speed of light is going to be the same wherever you go in the universe. So your unit of meter is not going to change under no conditions whatsoever. So that's basically what they have done. But for example, the kilogram is still not based on such definitions and such units, meaning that they have taken some iridium platinum cylinder, and they are keeping it somewhere in Paris, as far as I know, as far as I've read. And that is basically that is being kept under certain conditions, and that is basically our standard for a kilogram, right? But apart from that, basically everything else is fine. But we will get to the definitions shortly. Now, so now it is now defined as the distance light in a vacuum travels in 1/299,792,458 of a second. A meter is about 3 inches longer than a yard, which I don't really understand that readily. I mean, I'm not familiar with inches and yards, but we will get to that. Now, 1 meter is about 39.37 inches, or 1.094 yards. Longer distances are often reported. You don't really need to worry about these numbers. You don't really need to memorize them or anything. These are conversion factors. You will get the conversion factors in the table, and you can use them whenever you need to. And longer distances are often reported in kilometers, which you already know, whereas shorter distances can be reported in centimeters, for example, or millimeters, and so on and so forth. So the important thing here is to understand that basically a meter is defined as the distance light travels in a vacuum in 1/299,792,458 of a second. Okay. Now, of course, this is a valuable picture here, or graphic here, or illustration here, which is as you can see, this is 1 meter, which is 1.094 yards, which is equal to 39.36 inches, right? So we will talk about this. Okay, so now about this graphic. So you can see that you have 100, basically 1 meter, which is 100 centimeters, I suppose, 10, 20, 30, 40, 50, all the way up to 100 centimeters. And that is 1 meter. This is basically, I suppose, the same thing scaled up here to 1 meter, for example. And then you have 1 yard, which is the same thing as 1.09, approximately 1.1. Basically 1 meter is approximately 1.1 yard, meaning that 1 yard is a tiny bit less than a meter in terms of length, basically. And since basically, and that is 1 centimeter, all drawn to scale. So 1 centimeter is basically the same distance divided by 100, meaning that this is 1/100th of this length, and this length, which is 1 inch, is 2.54 centimeters. So it is 2.54 times this length over here. So that means that basically then 1 meter becomes 39.36 inches, right? Of course, there is a problem here, and that is, and then the problem is that usually there are important things that are not covered in a basic chemistry or in a basic physics course, and that is the problem of units. Earlier I was talking about those different systems of units. Well, as long as you're dealing with meters, centimeters, and kilometers, basically meters, you have no problems, you're good to go. Even if you're dealing with inches is some definition, you have no problem with that. 2.54 is a number, is a definition, and you have no problem with that. But then when it comes to conversion, for example, converting from yard to meter or well, inches to meter is again, well, we'll have to see about that, because you see over here, I do not really know how many significant figures, for example, this number has, or how many significant figures this number could have, because I don't really understand the other system that basically yard is a part of, right? So if I want to know basically if I want to know how to work with these numbers, I need to understand that system from which all of these numbers have come, and then if that's the case, then I know basically what to do with these numbers. Otherwise, there is always this type of confusion that you don't even know where the numbers are coming from, and so you don't really know what to do with the numbers. And that happens when it comes to the number of significant figures and the rounding numbers, and to so many significant figures and so on and so forth, which is a big, not a big problem, but a fundamental aspect of science. You need to know what to do with your numbers. But hopefully we will get over that problem. Let's see how that goes. We will work something out. So now this was the unit for length, which was basically based on the distance that light travels in vacuum in so many seconds. So that is basically 1 meter. So about mass, basically the standard unit of mass in the SI system is the kilogram, basically symbol K, lowercase k, lowercase g. A kilogram was originally defined as the mass of a liter of water. A cube of water. So a liter of water, as you know, hopefully, or probably, I don't know, but we will have basically everything about, we will have everything about a cube, and we will understand what it means to be 1 cubic meter, 1 cubic decimeter, 1 cubic centimeter, 1 milliliter, and so on and so forth. Now, what they have done is that back then, in the past, the kilogram was defined by a certain cylinder of, a kilogram was originally defined as the mass of a liter of water, a cube of water with an edge length of exactly 0.1 meter. 1/10 of a meter, meaning 10 centimeter times 10 centimeter times 10 centimeter. Imagine that you have a cube with that edge length, and then you basically fill that cube with water. The volume of that much water would be basically 0.1 times 0.1, basically 0.1 meter times 0.1 meter times 0.1 meter, which is the same thing as 0.001 cubic meter. That's 1,000th of a cubic meter, or basically 1 into 10 raised to the power negative 3 cubic meter. That's so much basically. That is the volume of the cube, or basically water. Now, so much basically that amount of water that has this much basically volume has some mass. Now, the mass of that water was previously defined as 1 kilogram. If you want to know basically how many liters that is, basically that's exactly 1 liter, because you see this is 0.1 meter is the same thing as 10 centimeter, right? So if you have a cube that has a edge length of, if you have a cube that has a edge length of 10 centimeter, so this is 10 centimeter, this is 10 centimeter, and this is 10 centimeter, the volume of this cube becomes V is equal to 10 centimeter times 10 centimeter times 10 centimeter, right? Which is equal to 1,000 cubic centimeter. 1,000 cubic centimeter. So 1,000 cubic centimeter is by definition 1 liter. If I'm not mistaken, let me check. What is 1 liter? So 1 liter is 1,000 millimeters. What? No. So here it says that the liter is a metric system of unit of volume, which is non-SI unit mentioned in the SI, it's equal to 1 cubic decimeter, 1000 cubic centimeter. As you can see, 1000 cubic centimeter. 1000 cubic centimeter, right? So this is again the same thing, meaning that, well, of course, 1,000th of a cubic meter is the same thing as, is exactly the same thing as 1000 cubic centimeter, because I got the same numbers, and because over here I had basically 1/10 of a meter times 1/10 of a meter times 1/10 of a meter, and then I simply took the numbers and converted them to centimeters, meaning that 1/10 of a meter is just simply 10 centimeters. So, which means that basically 1,000th of a cubic meter is the same thing as 1,000th of a cubic meter is the same thing as 1,000 cubic centimeter, right? And that is equal to 1 liter. Now, what they have done is that they have taken the mass of so much water, the mass of so much water, and defined it as 1 kilogram. And they have defined it as 1 kilogram. Now they have done this, and then, but they must have had problems with that. So a kilogram was originally defined as the mass of a liter of water, a liter of water, a cube of water with an edge length exactly 0.1 meter. It's now defined by a certain cylinder of platinum iridium alloy, that cylinder here. It seems that this type of alloy, basically platinum iridium alloy, is very stable, and I don't really know, basically not in scientific terms, but well, I would say in colloquial terms that I have read in these books, it seems that it's just a very, like the most durable kind of alloy that you could ever make, as far as we understand scientifically today, or something like that, or something to that extent. So it is now defined by a certain cylinder of platinum iridium alloy, which is kept in France. Now, any object with the same mass as this cylinder is said to have a mass of 1 kilogram. So 1 kilogram is about 2.2 pounds. The gram is exactly equal to 1,000th of the mass of the kilogram. Now, there is also a problem in science regarding gram, not in science, but probably only between people, that some people think that gram is the unit for mass, and then like other units, that you add kilo to that, and that becomes 10 raised to power 3 times that unit as a prefix. They think that gram is the basic unit for mass, and then kilogram becomes a prefix added to that. But surprisingly enough, it's not the case that the base unit for mass happens to be the kilogram and not the gram. I don't really know how that has happened or why, but that's actually interesting. So that is that. This replica prototype kilogram is housed at the National Institute of Standard and Technology, NIST, in Maryland. And now the unit for temperature, basically temperature is an intensive property. so we had two types of properties. We have intensive properties and extensive properties. We said that intensive properties were the kinds of properties that depend on the mass of the mass or the volume. I don't really remember. So here basically we said that if the property depends on the amount of matter present, it's an extensive property. The mass and volume of a substance are examples of extensive properties. I see. If the property depends on the amount of matter present, it's not necessarily the mass of the mass present, but the amount of matter present, and there is no way to know what that means. Now they have said that it's an extensive property. The mass and volume of substance are examples of extensive properties, and we argued over here that basically, for example, heat and temperature are examples of intensive and extensive properties because basically, for example, a drop of hot cooking oil has the same temperature as a pan full of basically hot cooking oil, but a drop of hot cooking oil, if it drops on your splashes on your skin, it's not going to be that big a deal. It's not going to be that much of a problem. But if the whole content of a hot pan basically containing hot cooking oil, basically if that is poured on your skin, then you're going to have severe problems, of course. And so basically in both cases, basically those two, the drop and the whole pan, have the same temperature, but of course the pan containing all the oil, the hot oil, is going to have much more heat, and therefore the heat is going to burn you. So what that means is that then temperature becomes an intensive property, meaning that it does not depend on the amount of matter present, but heat is an extensive property because it does depend on the amount of the oil present in that situation, right? So that was basically that. So over here we said that temperature is an intensive property, as we argued just a few seconds ago. The SI unit of temperature is the Kelvin with a capital K. The IUPAC convention is to use Kelvin, all lowercase for the word, uppercase K for the unit symbol, and neither the word degree nor the degree symbol. So this is important. The IUPAC convention is to use Kelvin, all lowercase, for the word, uppercase K for the unit symbol, and neither the word degree nor the degree symbol whenever you're using Kelvin, basically. So the degree Celsius is also allowed in the SI system, but with both the word degree and the degree symbol used for Celsius measurements. Celsius degrees are the same magnitude as those of Kelvin, but the two scales place their zeros in different places. We will see about that. Now, water freezes at 273.15 Kelvin or 0 degrees Celsius and boils at 373.15 Kelvin or 100 degrees Celsius. As you can see, 273.15 and 373.15, the difference of that is basically 100 Kelvin. and the difference between 0 and 100 is of course 100 degrees Celsius. So they have, the two scales are basically the same, but for whatever reason they are misplaced, so that's basically why the whole thing is basically different. So water freezes at 273.15 Kelvin or 0 degrees Celsius and boils at 373.15 Kelvin, 100 degrees Celsius by definition, and normal human body temperature is approximately 310 Kelvin or 37 degrees Celsius. The conversion between these two units and the Fahrenheit scale will be discussed later in this chapter. We will see all the scales and the conversion and everything in probably at the end of this chapter. Now, basically the unit for time is of course the second, and the SI base unit of time is the second. Small and large time intervals can be expressed with the appropriate prefixes. For example, 3 microseconds is 3 into 10 raised to the power negative 6 seconds, for example, and 5 megaseconds would be 5 into 10 raised to the power 6 seconds. We also have hours, days, years that can be used in the SI system. These are some units that have been added to the SI system, meaning that they may be used in the SI system. I will prepare a table of those units probably in the next video. Okay, so basically the next thing that we have here is, let me see if we can do this in the next video. Well, let's actually do the next part in the next video, because it's going to take some time, and we are actually done with time, so with this part which is about time, so we will talk about the derived SI units in the next video. I'll see you in the next video. Thank you.